Today we're going to take a look at some other applications of integration. There's some pretty cool stuff that you can do once you understand integration to um, take a look at some neat applications around the world and in mathematics. So the first one we're going to take a look at is calculating volume using some integration. So if we go back to the definition of the volume of a right prism, and that volume is the area of the base shape. So sometimes that's a rectangle, sometimes it's a cone, so it might be a circle, a cylinder is a circle, it might be a triangular prism. If you can calculate the area of the base, you just need to multiply it by the height. And it's going to tie into integration. Let's assume that we had a cone. If you took a really thin slice across the cone, you'd end up, and by thin slice we actually give it a little bit of height, so some delta change in that height, I'll call it dy, you'd have a really thin circle, and the area of the base of that circle is the circle times the height, which would be delta y. We can start to maybe see if we added up all those thin slices, an infinite number of them, we're really dealing with integration. So let's just put that down into some notes. And as I said, we can calculate the area of a complex volume, like this cone. It's not that complex, but by slicing it into very thin cross sections, each of which would be a very small right prism. We could calculate the area and we could multiply it by the height. And then we're going to take all of those cross sections and add them together. And as I said, this is really similar to adding up all the thin rectangles when we did integration under the area under a curve. So the volume gets calculated simply by taking an integration from a to b of the area formula with respect to the height. So if I go back to my cone here, I went up a certain amount. That's the area at y, and then I'm taking it with respect to dy, and I'm doing this a lot of times. I'm doing it all the way from a all the way up to b. That's why I've got the integral from a to b. That's doing it a lot of times, an infinite number of times, depending on the height, calculating the areas, and each little area had a difference of dy. So this part here is the area of a cross section. So let's take a look at an example and actually calculate something. And we'll start with one that we already know how to do, just so we can double check our work. You'll notice that using other methods, like the formula, will be way faster than doing this with integration. It's not until we get to more complex shapes that integration becomes the only way to do things. Calculate the volume of a pyramid, and it's got a square base with sides of 5 meters, and it's got a height of 15 meters. So here's my pyramid. And the old way of doing this was to use the pyramid formula, 1/3 of the area times the base, which is s squared, times the height. And this is a really fast way to do things. If you multiply this together, you get 125, and the units are meters cubed. Done. We'll take a look at how to do this with integration. You'll notice it's much more complicated, but as I said, when we get to more complicated volumes, this is really the only way to go about calculating them. So let's take a look at the cool way of doing it. First of all, we need to know what shape each cross section is. So if you cut a slice across here, you would end up with little tiny squares. So that's the first thing that we need to do. And we want to take a look at any square, so we want to take a look at the square that happens at height y. Well, the whole height was 15, and if I go up y, that leaves 15 minus y as the top part. So now I've divided my height into two pieces, up to y and above y. And now we can go about and try to find a formula for the area of this square at height y. To do that, we're going to use similar triangles. So the next step is to find that area formula, find it at height y, and in this case, to do that, we're going to need to use similar triangles to find that side length at that height. So to create myself a little bit more space here, using similar triangles, well, the base compared to the height of any similar triangle is the same. I've got one big triangle. If I cut it down the middle, show the other side just so you see. So the entire distance across the bottom is 5, but I'm just caring about half, and the entire height is 15. And then when I make my slice, my little tiny triangle, I've got a height of y, and this is 15 minus y from here to here. I want to know s, how far that is. Actually, that's half of an s, because on the other side is the other whole s. So I want to know what that side length is of my square. So just draw it one more time. I'm calculating that red part, but I need to double it, so I'm going to use half s. And the reason I need to double it is because I want to know how far it is for each of those side lengths at that particular slice. And as I said, the base and the height are the same in ratio, at least for these triangles. So the big triangle had a base of 2.5, but it had a height of 15, and then the other triangle, this little one, has a base of a half of an s, and the height is 15 minus y. And what I want to know is what's s. So by cross multiplying or by a little bit of algebraic manipulation, we can get what the side length is. And in this case, I'm doing 2.5 times 15 minus y, all divided by 15. That's what a half of an s is. And if I multiply it by 2, I get times this side by 2, times this side by 2, divide by 3. I end up getting 1/3 of 15 minus y as my s value. So the side length at arbitrary height y is 1/3 of 15 minus y, and I want the area formula. And this is a square, so the area is s squared, and in this case that's 1/3 times 15 minus y all squared, which is 1/9, and whatever 15 minus y squared is. Now, why I need that is because I'm now going to go and do an integration, and in this case the integration is going to call for, when I do my volume, I'm going to do an integral of my heights. So I started at 0 and I went all the way up to 15, and then I need my area of a cross section, which is 1/9 times 15 minus y all squared dy. And this formula will calculate, hopefully, to 125. So let's try it. 1/9, 0 to 15. If I expand this out, I get 225 minus 30y plus y squared dy. And calculating that, I get 1/9 of 225y minus 30y squared over 2 plus y cubed over 3, all getting evaluated from 0 to 15, which just means substitute in 15 for each of these values. And go ahead and do that on your calculator, and magically you get 125, and it's still meters cubed. This is the cool way of doing things. I know that it's way more complicated, but as I've said a couple times, when we get even more complicated shapes, this is the only way to do it. Alright, let's look at a couple other examples of some cool things with integration and applications.